All right, and next up, Jim Head is going to give a presentation, Prospects and Problems in Scientific Exploration at the Artemis Base Camp and Overview. Take it away, Jim.
Thanks a lot. I really want to point out, Clive would love to have been here. We agreed to do this together, but he is occupied with an International Ocean Drilling NASA NSF conference in DC, doing some really great work and talking about sample retrieval and all sorts of other things that are in a very relevant environment, a remote but very nearby environment that has a lot of relevance to sampling on the moon, et cetera. So he sends his regards. And he also urged me to remind you that actually I was chair of a SheSat in 2009, which addressed some of these basic issues. And so some of the questions that I'll address today are explored also in depth on the League site. Look for the 2009 SheSat report, and hopefully we can have that passed around later with the coordinates, et cetera. So that's another piece of history there, which is really relevant. It would have been continued, but the Constellation program took another direction, and then, of course, never came to fruition. So we have some themes here, which are really kind of important. So I want to talk today about, as you asked me to do, essentially prospects and problems in scientific exploration at the Artemis Base Camp. And I point out the Artemis Base Camp in a sense of ABC blocks because that's what it is. It's a fundamental structure there that we're going to be working from. And so we want to talk about both prospects and problems. Next slide, please. The prospects are fantastic. Okay, I am so excited since working in the Apollo program to come back and really go to these very, very different places. We're going to explore outside the Apollo Luna, Chang'e 5, 3 to 5 region. Okay, that's really important. And we're also going to be addressing transformative lunar science. I can only underline the large number of documents, including this one from Survey, Transformative Lunar Science, that outline the critical issues that we can address here. Okay, so there's no question. There's fundamental science to be done. It's challenging, as we'll get to, but it's really incredibly important. So the third thing, of course, is the possible volatile resources to support long-term human stays. This is really important because it isn't just like, okay, as I like to say, before you use that to flush the toilets, we need to look at those things and look at the origin and evolution of volatiles in the inner solar system. What an incredible record for the internal and external. That is stuff that's been erupted from volcanoes and stuff that's come in from meteorites is an incredible record. So both of those things are going to be really important. And of course, we also have to have solar power to survive lunar night over a period of time, because we can't really technically do that yet. I'm convinced that over the next couple of decades, minimally, okay, or I should say no, by the next couple of decades, we will have solved that problem, but that's what we need right now. Next, please. So if we look further, some detail here, okay, this is really the South Circumpolar region as a whole in which Artemis areas lie, and the landing site will be chosen for the ABC. This is, as Brad Jolliffe pointed out, there are two fundamental unexplored crustal terrains there, the Farside Highland terrain and the SPA terrain. And this really enhances our understanding of crustal stratigraphy. Our whole basis for science understanding of the moon isn't the early magma ocean model, and this will really let us understand something about the heterogeneity. And it also could provide access to mantle samples. It's one of the best places to go to look for that sort of thing. And so this will give us not only insight into chronology, but also into the impact flux, the age of SPA, dozens of craters and basins. And so that's all good news. The bad news about that is it's really complex. And we published a paper last year, Krasilnikoff et al., which is a new geological map. And I encourage you to take a look at that because we mapped all the craters in the broad area. And also we dated about 200 units in that, including a lot of the craters, et cetera. And we also looked at the sequence of events. So we have this whole sequence of events. And if you look in the lower right, the broad brown diagrams there, this is really important for the stratigraphy. So we have this for each of the sites, which will give us an idea of what samples we might be getting from what direction. And that's critically important because this is also really important for the Artemis Base Camp site selection and exploration strategy. Next, please. So it's all good news. It's all great news. It's going to be a tough job, but indeed, it's located within the SPA basin. I mean, take a look at this. Not only do we have the SPA basin, rim, if you will, and interior, but it fits within, as you see in the upper right-hand slide there, a whole series of missions like Apollo 15, Apollo 17, Apollo Luna 20, Luna 24, et cetera, and Apollo 14. This is all a context of how we understand these large basins. And we're going to have a really great job here for the South Polacan Basin to put that into context and learn from it. And a lesson here is that this whole region is much more similar to Apollo 16 Central Highlands, because we basically don't have a lot of Maury or other kinds of features that we can really tie our interpretations to. And so it's going to be a critically important thing to understand Apollo 16, because this is a complex impact polymeric breccia dominated geology, no question. And of course, on the basis of that experience, it requires integrated strategy for site selection, traverse planning, sample assessment, documentation, and analysis upon return. This is really critical. It's got to be all integrated. You just can't pick up a box of rocks, bring them back, say, okay, what happened? We need to understand provenance. Where do they come from? Next, please. So one of the things that I think we're going to be thinking is that the prospects, new terrain types in lunar far side, rim interior of ancient basins, possible buried ancient volatile record, opportunities for new and unique geophysics. This is really important. Okay, this is something that can really be done, in fact, with the Artemis Base Camp. Okay, in the two diagrams in the lower right here, you can see some maps of what was deployed on Apollo. Apollo did incredibly, you know, in Apollo 14, we had a Gatling gun going down, firing approximately charges down a seismic line to look at the shallow regolith. Apollo 17, we deployed, in fact, large explosive charges that were detonated after the astronauts left orbit. We were very careful about that. And, you know, incredible amount, you know, traverse gravimeters, all sorts of things that were deployed there. And we're going to be able to do this again and do it even more comprehensively with increase in technology, gravimeters, magnetometers, heat flow experiments, lunar lasing, LR cubes, okay, et cetera, et cetera. This is really critically important. And of course, lessons for feed forward to Mars. As Châtel was pointing out, this is what it's all about. We need to be thinking about this. What are the lessons for feed forward to Mars? And one of the main ones is optimizing astronaut situational awareness and heeding Krikolev's creativity versus determinism. Sergei Krikalev pointed out in a paper in Astronomical Journal that whatever, I'll put it in the chat, that basically we've been thinking about determinism because of the way the ISS works, and we haven't been engaged in surface exploration where the creativity comes in. It's not that the astronauts aren't creative in the ISS. It's just when you're out on the surface, you really need to be thinking. Not only that, we're not going to be able to communicate with them on Mars, okay, in a direct sense, okay, because of the delay time. So we're going to have to be thinking about this, okay, and it's really kind of important to be able to let them do their thing, exercise their situational awareness at the Artemis Base Camp, and not meddle with them 100% of the time, so that they can, in fact, feed forward to essentially the situational awareness that they'll have to have in the long-term duration exploration of humans on Mars. Next, please. So let's talk a little bit about problems. Well, here's one of them, okay? I love this picture here because it's Dorothy and the Wizard of Oz. Wow, we're not in Kansas anymore, Toto. Toto's got it under control. Toto is locked onto the little munchkins there. You can just see that sort of like, oh, this looks like lunch to me. But the key is we're just really not in Kansas anymore, okay? And we need to think about that, okay? Next, please. So if you think about that, here's some problems, okay? I want to outline 10 problems very quickly for future discussion in our breakout groups, et cetera. Constantly changing illumination geometry and thermal environment. This is really, really critical for the amount of EVA time we have, the amount of traverse planning, the nature of traverse planning, and real-time options as you get moving around the surface is just really, really critically important. And it's going to be a challenge we've never faced before. We have extremely complex geology, multiple overlapping ejecta deposits. How do we establish provenance? I mentioned these stratigraphic columns here, and there is information there, but it's going to be a statistical problem, and we need to spend a lot of time doing the sampling and thinking about what we're likely to have, and then finding out where we can get it so we can establish the stratigraphy and the provenance. We also immediately need mobility and extended sorties. There's just no question about that. If you take a look at the Apollo 15 lunar roving vehicle there on the right, and then look over at that chart, basically, you can see how on Apollo 15, 16, and 17, it incredibly increased the total traverse distance that they were able to go. And if you look, these are all not in radii, these are all in total traverse distance. So you can see how limited the walking traverses were. So we need that. We need it for sampling, for exploration, experiment deployment. You take a look at Apollo 11 to 14 compared to 15 and 17, which are real scientific expeditions. We also need to preserve the environment. Pascal Lee will talk also about this a little bit too, but I've had 5 field seasons in Antarctica, and it's absolutely amazing, but the credo is take nothing but photos and leave nothing but footprints, and try not to leave those. We're going to be spending a lot of time at the Artemis Base Camp, and if you take a look at the lower right, you can see the effects of the movement around the surface of one particular landing site, and we don't want to tread over everything. We're going to want to have that pristine, so we're going to establish pathways, et cetera, that are going to be really critical. That's got to be top on the agenda in terms of protecting the environment for further scientific exploration. Next, please. In addition to that, there's highland slopes. Now, people think, oh, well, Apollo 16, it'll all be fine. No, no, no. That was the Cayley Formation. It was largely flat plains. What you see in the upper left there is Dave Scott on the slopes of Hadley Delta, and on the right, Jack Schmidt and Gene Cernan at the slopes of South Massif, okay? And believe me, this was really difficult. You go back to the Lunar Surface Journal, you'll see that this is not trivial. They had real problems both with walking and also with roving. We need to take this into consideration and treat this and learn about this. Not only that, when you get up these slopes, you have this kind of like elephant hide terrain, and that is really rough going. So we have a lot to learn there. It's a challenge. It's a big problem that we need to resolve, okay? And we need to do experiments right away when we get there to see how we can overcome those and get good traversability and so on. 7, how to plan and optimize access to PSRs. That's what can I say? Human, not right away, okay? Robotic, yes, but how do you coordinate those? And what do you do? How do you get the samples back? What do you do? We will see soon, we hope, that the rover mission Viper will really help us with that, but there's a lot to learn there. Number 8, lunar dust and accumulation with time. Shown on the right there is the Apollo 14 A7L suit that was worn on the moon. And Ron Creel is always rightfully harping on the fact that this is a real problem. It's a real problem, okay? So we need to address that. We can't just ignore that. It's going to be a big, big problem, because if the astronauts are going to be on the surface a long time and going out again and again in an Artemis base camp, they may have to have suit changes, okay, a lot, okay, because right now I don't think we're dealing with it, unfortunately, in the most ineffective way. People are thinking about it. A lot more needs to be done. Sample return down mass bottleneck. This is number 9 here. So Orion has about a 50 kilogram sample return capability. Now, why is that? Well, because Orion wasn't designed initially. It's a piecemeal, if you will. It was not designed originally to bring samples back and to go down to the surface and bring samples back as it was done on Apollo and transfer them, et cetera. So there's an issue there. It can only bring back about 50 kilograms of lunar samples. There are other samples, biological samples, and things that need to be done too. And this is about the same as Apollo 11, 12, and 14. And does that mean we have to triage samples on the surface or in the, in orbit? Or this is not the way to go. I mean, it will take 8 Artemis missions to collect 6 Apollo missions collected. We got to do better than that. And I think people are thinking about this, but that has to be top priority, because even though technology has increased capability immensely, we still cannot do on the surface or in orbit what we can do back here on the Earth. You have to return the samples, and they have to be can't be a grab bag. Number 10, up mass burden and resupply rate. This is another problem, okay? ISR is looking at this. You don't want to take cinder blocks and bricks up, okay? So ISRU is critically important, but we also need multiple concepts. We've been working on synthetic biology using myco-architecture, essentially mushroom growth in situ with local materials to build a block like you can see with the one inscribed by NASA, with NASA. There are other interesting capabilities that we might be able to utilize to solve the upmass problem. It's huge if you're going to have resupply of an Artemis space camp and beyond. Next, please. We're lurching to a solution here, okay? So I just have this last couple of slides here, lessons from the past for the future. George Santayana has said, those who cannot remember the past are doomed to repeat it. But Kurt Vonnegut said, I got news for Mr. Santayana. We're doomed to repeat the past no matter what. That's what it is to be alive, or that's what it is to be human. And it's probably true, sadly. But I like Mark Twain's. History doesn't repeat itself, but it rhymes. Next, please. So here's some points to make that I want to kind of like put out in a final analysis here. There's this thing called institutional amnesia. All institutions have this, okay? So if you think about Vietnam, the lessons from Vietnam as we went into Iraq, almost forgotten, okay? Oh, we're going to reinvent the wheel. It's different now, et cetera. There's also the Apollo constellation Artemis. There's a little bit of amnesia there. I've heard statements such as the Apollo is flags and footprints. We're not doing that. That was flags and footprints. This is a myth, okay? And I think it's really important not only to not say that because it's just totally untrue, but to actually turn your head around and say, hey, we can really learn from what was going on. Apollo 15 was arguably, okay, a Lewis and Clark like the first scientific expedition to the moon, okay? So this is really important. Happy to come back anytime and talk about this because the increase in capability working shoulder to shoulder with the engineers was fantastic over the Apollo program. Secondly, distributed architectural element strategy. In Apollo, we did ABC, okay? Lunar module, command surface module, return vehicle, et cetera. And, this let us, we knew what the letters, we had 26 letters, if you will. We could put them together in the blocks, okay? And Artemis is not like that. It's very different, okay? It's okay. It's, it'll be successful. It's just a different way to look at it. And we need to be thinking in those terms because as Chattel and others have pointed out, it's an evolving architectural elements, but how will they be coordinated? The ESSIO is tasked with doing that sort of job, but it's really complicated. It's much more like a Rubik's Cube. We can solve a Rubik's Cube, okay? But it just takes more work and a different approach than basically building the blocks, okay? So that's a different way of doing business. You need to think differently about that. All of us do to interact with that. We need to work shoulder to shoulder with the engineers. Another thing is the dry hole fork in the road, okay? So, I'm hopeful well, I'm a scientist, so I'm not optimistic. I'm hopeful based on preliminary data that we're going to find water ice in the subsurface in a permanently shadowed regions. But I don't know that we are. And I think we all need to be ready to think about the fact that we may end up with essentially a dry hole. And what do we do then? Is that we still want to go to the South Circumpolar region, or do we want to move to more equatorial regions like the Chinese are going to be doing for their landings, okay? For their human landings. They're going to equatorial mid-latitudes, okay? Maybe we need to go back there, okay? There's plenty to do there, believe me. Then we've been working on a 500-day mission to, in fact, the Hadley-Apennine region to think about how we would go back and then feed forward to extended stays on the moon and extended stays on Mars. Next slide, and this is the last one, I think.
And Jim, we do need to wrap up to move on to John.
Absolutely. So this is a chart that just shows the red circle there. It is indeed a couple kilometer radius, and this is the walking distance around Apollo 11, 12, and 14. You can see how with robotic and rovers, human rovers and robotic rovers were able to increase that out to 14 or so kilometers, and this is really critically important. And I just point out, as Dean Epler reminded me yesterday, that all our traverse planning is being done now with robotic rovers. We have almost lost, with a couple exceptions, we almost lost all people with experience with human traverse planning experience. So we need to be thinking about that and do extra homework. And the last slide, which is indeed the last slide, next please, is in fact, the past is prologue, okay? We're not going to do Apollo again, but heeding Mark Twain, essentially, history doesn't repeat itself, but it rhymes. So I hope we learned lessons for that. We have great things to go to in the future. And I'm just totally psyched to go forward to the moon and then on to Mars. Thank you very much.